What if the world is spending $80 billion building AI data centers that can't even turn on? That's exactly what's happening right now. Microsoft is investing $80 billion in AI infrastructure this year, but entire pods of H100 GPUs in Virginia and Arizona are installed and waiting offline because the power grid can't support them. Meanwhile, TSMC controls over 90% of the 3-nanometer chip production essential for frontier AI, and a single company in the Netherlands, ASML, is the only manufacturer of EUV machines capable of making these chips, producing just 55 units per year, while demand exceeds capacity every single quarter.
But here's the real shock. Even the GPUs that are powered on are sitting idle up to 55% of the time. ML Commons reports that elite H100 clusters average just 45 to 65% utilization, billions of dollars in cutting-edge hardware burning electricity while waiting for jobs to schedule, data to load, or cooling systems to catch up. China has restricted exports of 80% of global gallium and 60% of germanium, the rare materials that make AI chips possible. The Middle East has built exaflop-scale clusters running at under 40% capacity. Europe's data centers hit 70% utilization, but can't build fast enough due to 18-month permitting delays.
The bottleneck isn't chips. It's not even money. It's power, plumbing, and utilization. And until we solve that, every new GPU shipped is only half the solution.
Welcome to AI Decoded, the podcast where we demystify artificial intelligence and explore how it's transforming our lives, our work, and our future. I'm Emma Clark, and I'm thrilled to be your guide on this journey into one of the most transformative and fascinating technologies of our time. But before we begin, we want to share something that makes this show unique. AI Decoded is the first podcast about artificial intelligence created by supervised artificial intelligence. Yes, you heard that right. Each episode is designed, structured, and produced with the help of AI, always under the supervision of human experts. The result? Up-to-date, accurate content focused on what you really need to understand and apply.
And I'm Michael Reynolds. Whether you're already an AI enthusiast, a tech professional looking to stay ahead of the curve, or just someone curious about the buzz surrounding AI, this podcast is for you. We're here to break down the complexities, demystify the jargon, and show you how AI is changing the world, one innovation at a time.
We tend to think of AI infrastructure as software that runs on GPUs. But before we even get to the chips, there's an entire industrial backbone, from rare earth mining to silicon wafer fabrication to packaging innovations that make GPUs fast enough to train massive models.
Exactly, and here's the kicker. Most of the bottlenecks in AI infrastructure today start way before the GPU even hits a server rack. We're talking about materials, machines, and factories, each one with its own supply-demand tension. So let's begin at the beginning. What materials are critical to AI hardware? And are we producing enough?
To manufacture chips for AI workloads, we rely on a handful of rare, often geopolitically sensitive elements. Gallium, used in high-speed semiconductors for power efficiency. Germanium, critical in optical interconnects and high-mobility transistors. Cobalt and nickel, essential in power and heat dissipation layers. Neon, used in the lasers for advanced chip engraving. And of course, ultra-pure silicon, the base material of all modern processors. Here's where it gets tricky. Over 80% of global gallium and 60% of germanium refining capacity is controlled by China. In 2023, China began restricting exports of these materials in response to U.S. tech sanctions. And those restrictions remain in effect in 2025.
Let's put this in terms of AI-specific demand. According to the Semiconductor Industry Association and Accenture, AI chip production, especially high-performance accelerators, requires about 3 times more gallium, 5 times more cobalt, and significantly more HBM per unit than legacy consumer CPUs. And here's the imbalance. The world is producing enough of these elements for total semiconductor output, but not enough to support the AI-specific demand curve, which is growing 70 to 100% per year. So the constraint isn't, can we make chips? It's, can we make enough of the right kind of chips fast enough?
Once we get the raw materials, the next step is fabrication, where those elements are transformed into wafers and etched into chips. Let's talk about the factories that do this. These are the wafer fabs, and building one takes $15 to $25 billion and up to 3 years. Only a handful of players operate at the leading edge, meaning chips smaller than 7 nanometers. TSMC in Taiwan, the undisputed leader, Samsung Foundry in South Korea, and Intel Foundry Services in the US, now trying to catch up. In 2025, TSMC controls over 90% of global production at the 3 nanometer and 5 nanometer nodes, which are essential for chips like NVIDIA's H100 or Apple's M4.
And the bottleneck isn't just funding, it's tools. The most advanced chips are made using EUV lithography. That's extreme ultraviolet light used to engrave incredibly fine features. Only one company in the world makes EUV machines, ASML, based in the Netherlands. Each machine costs about $200 million, and ASML can only build approximately 55 EUV units per year globally. Compare that to the demand. According to ASML's CEO, orders have exceeded capacity every quarter since 2023, with AI fab demand now representing 70+% of new orders.
So the math's not looking great. Here's how it breaks down regionally. Taiwan, TSMC, approximately 65% global share and approximately 95% utilization. South Korea, Samsung, approximately 20% global share and approximately 80% utilization. US, Intel Foundry, 10% mostly in ramp and 50% utilization. Europe, Global Foundries, 5% total and not AI-grade nodes. So here's the key insight. We're not short on total wafer capacity, but we're very short on AI-suitable wafer capacity at 3 nanometers or below, especially in non-Taiwan regions, which makes the geopolitical dependency even sharper.
Let's talk about the final stretch. Once chips are made, they still need to be packaged. And this is where AI workloads have changed the game. Traditional chips were built monolithically. Now we use chiplets, smaller compute modules that are tiled or stacked together to function like one big brain. But this requires advanced packaging technologies like CoWoS, TSMC chip-on-wafer-on-substrate, Foveros, Intel 3D stacking, EMIB, Intel Embedded Multi-Die Interconnect Bridge. The problem? Packaging capacity hasn't kept up with AI chip volume. According to Yole Group, global advanced packaging capacity needed to grow 80 to 100% year-over-year in 2024 to 2025 to keep pace with AI demand. But actual build-out only achieved approximately 60% due to cleanroom bottlenecks, thermal stacking challenges, and a shortage of trained packaging engineers.
So we're making wafers faster than we can package them. And that leads to delays of 3 to 5 months between fab-out and deployment for chips like NVIDIA's H100 and AMD's MI300X. And now we get to the other monster in the room, HBM high bandwidth memory. These are stacked DRAM layers that sit right next to the processor die and enable 1 to 2 terabytes per second of data throughput. For training large AI models, that kind of bandwidth is non-negotiable. Here's the constraint. Only 3 companies produce HBM globally. SK Hynix, 50 to 55% market share, Samsung, and Micron. In 2025, AI chips consumed over 75% of all HBM3 and HBM3E output, up from approximately 30% just 2 years prior, and demand is projected to double again by 2026. So are we underproducing? Yes, but narrowly. TrendForce estimates that global HBM supply in Q4 2025 is meeting approximately 85 to 90% of current demand. But major hyperscalers like NVIDIA and Amazon have pre-bought 100% of 2026 output. That leaves startups and smaller labs priced out or stuck on older chip versions. At the base of the AI infrastructure stack, are we overbuilt or underbuilt?
Great question. Let's break it down per layer. Raw materials. Global output is just enough for general chip demand, but AI-specific materials like gallium, neon, and HBM are tight, with China controlling multiple choke points. Wafer fabrication. Total global capacity is rising, but AI-suitable nodes, 3 nanometers, 5 nanometers, are concentrated in Taiwan and already near saturation. The US and EU are years behind. Advanced packaging, severely constrained. Lead times are long and throughput isn't scaling fast enough. HBM. In chronic shortage, production is booked out and demand from AI doubles every 12 to 18 months.
So while we may appear to be investing massively, the supply chain underneath is still under tension. AI needs a faster, cleaner, and more diversified foundation, or else we'll keep building castles on sand. We've talked about the materials and the fabs. Now let's move one layer up, the actual chips used to run AI models. Let's start with the most common term people hear, GPU. What exactly is it? And is it the only option?
Great place to start. A GPU, or graphics processing unit, is a massively parallel chip originally designed for rendering images. But today, it's the workhorse of deep learning, because it's optimized for the kind of math that underlies neural networks, matrix multiplications, and tensor operations. But GPUs aren't alone anymore. The broader category is called accelerators that includes GPUs, like NVIDIA's H100 or AMD's MI300X, tensor processing units, Google's tensor processing units, custom chips like AWS Trainium, Microsoft's Maya, and Meta's MTIA, and specialized silicon from startups like Grok, Cerebras, or Tenstorrent. These are all designed to do one thing: speed up the training or inference of AI models, faster than a general-purpose CPU ever could.
So, how many of these chips actually exist? And are we building enough to meet demand?
Let's talk numbers. In 2024, the world shipped around 3.8 million AI accelerators across all types. That includes GPUs, TPUs, and custom ASICs. Of those, over 70% were NVIDIA GPUs. In 2025, NVIDIA alone is expected to ship approximately 5.5 million accelerators, including 3.5 million H100 and HS200, 1.2 million of the new Blackwell B100, 800K older A100s who are still sold to inference buyers. That means NVIDIA controls about 80% of the global AI accelerator market, with AMD at approximately 10%, Google AWS at approximately 5%, and startups and others making up the rest.
The constraint isn't number of units, it's usable compute measured in training capacity. Let me explain. The largest training runs, like GPT-5, Claude 3.5, or Meta Llama 3, consume tens of millions of GPU hours. For example, training GPT-4 level models took around 25,000 H100 equivalent GPU running for 3 to 4 months. If you multiply that out, even 5 million shipped GPU isn't that much, especially when those same GPUs are also being used for inference, fine-tuning, API workloads, government and military programs, and AI PC backends and edge inferencing. And here's the demand curve. According to S&P Global, AI training compute demand is growing 2.5 times per year. At current shipping rates, supply is lagging demand by approximately 30% in usable compute hours, even though unit volume is growing.
So where are these accelerators actually going? Rough estimates for 2025 deployments. US, mostly hyperscalers, 55 to 60%. China, approximately 15%, mostly domestic chips due to export controls. Middle East, UAE, Saudi, Qatar, approximately 10%. EU plus UK, approximately 7%. Rest of Asia, Japan, Korea, Singapore, approximately 8%.
That puts most of the world's usable compute inside a few corporate clouds and 3 countries. And it introduces a second constraint. Even if you have the GPUs, can you use them efficiently? That's where interconnects and cooling come in. Let's start with interconnects. What are they, and how do they affect AI performance?
When we train large models, we're not running them on one chip. We're running them on clusters of 8, 16, 128, sometimes 1,000 plus accelerators all working together. Those chips need to talk to each other constantly, sending gradients, activations, weights, and memory cache. This communication happens over interconnects, basically superfast data highways inside the rack and across the cluster. The two big technologies are the InfiniBand, NVIDIA's high-performance interconnect, RoCE RDMA over Converged Ethernet, used by AWS, Azure, and others for custom networking. If the interconnect is too slow, chips spend more time waiting than computing, which drags down utilization.
So you could have thousands of GPUs and still get mediocre performance. And in fact, that's happening. According to a 2025 report from ML Commons, cluster-scale GPU utilization in production environments ranges from 45 to 72%, depending on interconnect efficiency, and the bottleneck is growing. Optical transceiver supply is behind schedule, especially in the US and Europe. And then we hit the last layer, cooling. Air just isn't cutting it anymore. Each NVIDIA H100 can consume up to 700 watts under full load. Multiply that across a pod of 512 GPUs, and you're drawing over 350 kilowatts of heat, which needs to be dissipated constantly. The industry is moving toward liquid cooling as the standard. Direct-to-chip cold plates, immersion cooling, servers submerged in dielectric fluid, rear-door heat exchangers with high-pressure loops. According to JLL's 2025 Data Center Outlook, over 60% of new AI-focused data centers commissioned in 2024 to 2025 are being built with liquid cooling as a default. But here's the constraint. Retrofit costs for older air-cooled data centers can exceed $1.5 million per megawatt, and timelines can stretch to 12 to 18 months.
So it's not just a chip constraint, it's power plus plumbing plus engineering. Let's bring it all together. Are we overbuilt or underbuilt at the accelerator layer? Let's go layer by layer. Accelerator unit volume. Adequate volume from top vendors, NVIDIA, AMD, but nearly all locked into hyperscaler pre-orders. Startup and academic access is severely constrained. Usable compute hours, underbuilt. AI demand is growing 2.5 times per year, while usable compute is only growing approximately 1.8 times due to utilization limits and interconnect lag. Interconnects lagging behind chip progress. Optical supply chain in the US and EU is behind demand. InfiniBand demand outpaces production. Cooling infrastructure split. New builds are fine, but legacy data centers are struggling to retrofit. Okay, we've covered what it takes to build AI infrastructure from the ground up. We've talked raw materials, wafers, chips, cooling, everything. But now we flip the equation. Who's actually using all this? Where is the real demand coming from?
That's the golden question. Because for infrastructure to matter, it has to be used, and used well. And AI demand is not one monolithic blob. It comes in three very different forms. Training, which is building the models from scratch. Inference, which is using the models after they're trained. Edge AI, which runs models directly on devices like phones or cars. Each of these has different hardware needs, different cost profiles, and very different impacts on infrastructure. Let's start with training. This is the part that grabs headlines. When you hear that GPT-5 took tens of thousands of GPU and months to train.
So let's explain this clearly. Training is when you take a blank model, think of it like a newborn with zero knowledge, and you feed it billions or even trillions of examples. Text, code, images, conversations. The model starts off randomly guessing, and with each example it adjusts its internal parameters, called weights, to get a little smarter. It's like teaching a student. But instead of lectures, you're feeding the model 300 billion flashcards and making it study nonstop for 90 days. And it's brutal on infrastructure. It's the most demanding thing you can do in AI. Let me give you an example. Training a GPT-4 scale model in 2024 took about 25,000 GPUs running 24/7 for 3 straight months. That's millions of GPU hours, and it consumed enough electricity to power a small city. And only a few players can afford to do that. It's incredibly capital intensive. So you have maybe 10 to 12 companies worldwide doing frontier model training at scale. Think of names like OpenAI, Google DeepMind, Meta, Anthropic, xAI, and some national labs like the UAE's G42 or China's BAAI also train large models with government backing. But here's the catch. Even with billions being spent, training demand is outpacing infrastructure availability.
So, how far behind are we?
According to estimates from S&P Global and multiple hyperscaler disclosures, training demand is growing at roughly 2.5 to 3 times per year, while usable compute capacity is only growing at around 1.7 to 1.8 times per year. And that gap is widening. You've got companies lining up with massive models, but they can't get time on high-end GPUs because NVIDIA's top chips, like the H100 and B100, are booked months in advance. And not just booked, prepaid. Cloud providers like AWS, Microsoft Azure, and Oracle are pre-buying entire production runs just to secure capacity. So if you're a startup or even a mid-sized lab, you might wait 3 to 6 months just to start training. So when we say training demand is high, we're not just saying people want to build models. We're saying there's a literal line outside the factory, and that line is getting longer. What's more, training workloads are what drive the need for supersized clusters. Hundreds or thousands of GPUs, fast interconnects, ultra-efficient cooling. So when you hear about energy-hungry data centers in Virginia or Arizona, Most of that footprint is being built to serve training runs.
Okay, so that's training. Big, powerful, expensive. But what about inference? This is where people actually interact with the models. Inference is when the model's already trained. And now it's answering your questions, writing your email, generating an image, or predicting a trend. It's what happens after the model has learned. Think of training as writing a book and inference as reading from it, but doing it billions of times a day. So inference is lighter per request, but massive in scale. Serving a single ChatGPT query might only take milliseconds. But if you're getting 10 billion queries a day, that adds up. Inference has its own set of demands. It requires low latency. You can't make people wait. It has to run reliably 24/7. And it's often deployed across hundreds or thousands of servers, globally distributed. And that creates its own kind of strain. According to McKinsey's April 2025 report, inference now accounts for over 60% of total AI infrastructure operating costs, even though it uses only about 30% of raw compute hours. Why? Because you have to build for peak demand, not average. That means buying extra hardware just to ensure users don't get delayed responses at 3 p.m. on a Monday. And the more people use AI-powered apps, chatbots, copilots, image tools, the more capacity is needed to serve them in real time. That's why cloud inference clusters are now being built in Tier 2 regions like Malaysia, Ireland, and Chile to serve traffic close to users and meet compliance and latency goals.
Now let's talk about the third demand layer, Edge AI. This one gets less attention, but it feels huge. Edge AI means running inference on the device itself, on your phone, your car, a factory sensor, without going to the cloud. Why? 3 reasons. Latency, edge responses are near instant. Minus privacy, no data leaves the device. Cost dash. You don't pay cloud fees for every interaction, and this is where things like neural processing units come in. NPU stands for Neural Processing Unit, a specialized chip optimized for running AI workloads locally with very low power consumption. You'll find them in Apple's M3 and M4 laptops, smartphones using Qualcomm's Snapdragon X Elite, Tesla's onboard FSD computers, industrial robots, and surveillance systems. In 2025, over 1.2 billion devices shipped with onboard AI acceleration. That includes phones, laptops, cars, and even medical equipment. So even though it's off the cloud, Edge AI is still infrastructure, it's just distributed. It reduces pressure on centralized GPU clusters, but it creates new demands on software, battery life, and on-device compute. And remember, the models that run at the edge are smaller, but they still need to be optimized and distributed. That's a huge part of the AI deployment workflow.
Okay, we've seen that AI infrastructure is being built at an unprecedented pace. We've seen where the demand is coming from, training, inference, and the edge. But here's the twist. Even with all this demand, a significant portion of AI infrastructure is sitting idle. We're not using what we've already built. And this isn't just a hardware issue, it's a systems efficiency problem. The question is no longer, do we have enough GPUs? It's, are they actually running workloads or just burning electricity while waiting in line? Utilization is the measure of how effectively our infrastructure is being used. For GPUs, that means, are they actively processing model workloads? Or are they idling because of data pipeline delays, scheduling gaps, software bottlenecks, or thermal constraints? It's like having a kitchen full of chefs and ingredients, but only a few dishes are actually getting cooked because someone forgot to turn on the oven or order plates. So utilization isn't about what's installed. It's about what's actually doing work. And here's the shocker. According to ML Commons and internal data from multiple cloud providers, even high-end clusters using H100s are averaging between 45% and 65% effective utilization. That means almost half the potential compute capacity is being wasted. So what's holding things up? Why aren't these incredibly expensive chips being used around the clock?
Several reasons. Scheduling delays. Most AI jobs are not scheduled efficiently. If a cluster has 512 GPUs but only 480 are used, the rest sit idle, sometimes for hours. Data pipeline bottlenecks. Training doesn't just need GPUs, it needs fast data access. If your dataset lives on slow storage, the GPUs wait for I/O. Networking and interconnect gaps. If your accelerators can't communicate fast enough, say because your InfiniBand is overloaded, You hit synchronization lag, dash power and cooling caps. In some regions, GPUs are throttled to avoid overheating or exceeding local grid limits, so even if they're technically on, they're not running at full performance. Software stack immaturity. Models don't always scale linearly across clusters. Poor code or unoptimized frameworks waste compute cycles. And this varies a lot by region. Let's walk through it. In the United States, hyperscalers dominate capacity, but power grid saturation, especially in Northern Virginia and Phoenix, is capping usage. Some new data centers have GPUs installed but offline, waiting for substations to be commissioned. Estimated average GPU utilization in high-density clusters, approximately 55%. Europe is more efficient on average, but with smaller capacity. Permitting delays limit supply, but what's built tends to run hot. Utilization often exceeds 65 to 70%, especially in Northern Europe. But thermal regulations in Germany and the Netherlands are now limiting rack density to avoid local overheating. China's usage is bifurcated. Domestically built accelerators like the Huawei Ascend 910B are deployed at scale but with lower software efficiency. Utilization in large academic and state clusters averages approximately 50 to 60% but is improving. South Korea and Japan have smaller but more tightly optimized clusters, averaging approximately 70% utilization. Middle East, UAE, and Saudi Arabia have massive new builds. Sovereign clusters like G42 Stargate have excess capacity built ahead of demand. Utilization in 2025 remains below 40%, but expected to rise by 2026 as local workloads catch up.
Now, let's talk about power, because even when a GPU is doing work, there's a huge difference between running at 60% versus 95%. AI infrastructure is now responsible for over 3% of global data center energy usage, and that number is climbing fast. Here's the kicker. When GPUs run at 60% utilization, they still consume approximately 85 to 90% of their peak power draw. That means you're paying for electricity even when you're not getting full performance. And globally, that adds up to hundreds of megawatts of wasted power. This isn't just bad economics, it's a carbon issue too. So if utilization is this important, are we at least tracking it well?
Sadly, not really. Few companies publicly disclose cluster-level utilization rates, and even fewer optimize their job queues or rebalance workloads across time zones. But there's movement. OpenAI, Meta, and Google are investing in multi-cluster job distribution, which means shifting workloads to clusters with free capacity, lower power rates, or cooler ambient temperatures. So if I had to summarize it in one sentence, it would be, we don't have a chip shortage, we have a utilization problem. We have more AI hardware than ever before. But too often, it's underused, poorly scheduled, or stuck waiting on power, bandwidth, or code. And until we fix that, every new GPU shipped is only solving part of the problem.
And it's not just about ROI, it's about energy, access, and scale. Utilization is the next battleground. And the players who win there, who squeeze every drop of value out of their infrastructure, are the ones who'll win the next phase of the AI race. Now, let's ask the big question. Are we overbuilt, underbuilt, or just misaligned?
Yeah, this is where it all comes together. Because when you look at the infrastructure stack in isolation, everything feels either overloaded or behind. But the truth is, it's not one story. It's 4 stories. Each region has its own balance, or imbalance, between what it's built, what it's using, and what it actually needs. Let's start at home. The US has built more AI infrastructure than any other country, by far. In 2025, over 55% of global H100 class accelerators are deployed on US soil. Hyperscalers like Microsoft, Amazon, Meta, and Google have pre-committed tens of billions in build-out. Now, Microsoft alone is spending $80 billion this fiscal year to expand its AI data centers. But here's the constraint: power. The largest US grid, PJM, just released a report stating that AI data centers alone will consume 32 gigawatts of new demand by 2030. That's like adding the energy footprint of entire cities just for compute. So we're not running out of chips, we're running out of electricity. New data centers in Virginia, Arizona, and parts of Texas are built, stocked with GPUs, and waiting for grid upgrades. In some zones, there are entire pods of accelerators that have been installed but never powered on. So is the US overbuilt? Not exactly. The hardware's there, but usable infrastructure is power constrained. which means utilization is artificially capped, even though demand is huge.
What about Europe?
Europe's in a very different situation. It's behind on total capacity, but what it builds, it tends to use very well. Here's the story. The EU was late to hyperscaler-scale AI infrastructure. Most large training clusters are still hosted in Ireland, France, Sweden, and Germany. Strict sustainability regulations cap rack density and thermal output. Permitting processes in places like the Netherlands and Germany take up to 18 months for approval. But the upside? European clusters have higher average utilization, often over 65 to 70%, because what gets built is usually oversubscribed from day one. Europe is underbuilt, highly efficient, but slowed down by bureaucracy. And that means AI researchers and startups often end up renting compute from US or UK clouds at higher latency and higher cost.
Let's talk about China. They've got their own situation with chip access, right?
Due to US export controls, China has limited access to top-tier accelerators like NVIDIA's H100 and H200. But instead of standing still, they've responded with an aggressive domestic strategy. Companies like Huawei and BioNTech are now producing homegrown accelerators. The Ascend 910B, the 104. Massive sovereign compute clusters are being built around Beijing, Shanghai, and Shenzhen. China's Ministry of Science and Technology estimates a doubling of AI-specific compute capacity between 2024 and 2026, but all on domestic hardware.
But are those chips as powerful?
Not quite. Benchmarks suggest that China's top domestic accelerators are 1 to 2 generations behind NVIDIA's Blackwell or AMD's MI300X. And because much of the open-source ecosystem is optimized for CUDA, NVIDIA's platform, software stack inefficiencies reduce actual throughput. So utilization isn't bad, but performance per watt is significantly lower. China is effectively building in parallel, but under technological constraints.
So would you say they're overbuilt or underbuilt?
They're capacity-rich but performance-limited. It's an intentional hedge. If export restrictions tighten further, they still have compute sovereignty, but it comes at the cost of efficiency.
And finally, the Middle East, specifically the UAE and Saudi Arabia.
This is the most ambitious build-out per capita on the planet. Abu Dhabi's G42 Stargate cluster is aiming for approximately 5 exaflops of training compute. Saudi's NEOM project includes AI-first smart infrastructure zones. Qatar and Oman are funding sovereign AI training labs with direct GPU imports. But here's the issue. Local demand hasn't caught up yet. These clusters are meant to serve future regional use plus potential compute exports. As of mid-2025, estimated utilization across UAE AI clusters is well below 40%. Much of the infrastructure is powered, cooled, and online, but running at partial load. The Middle East is doing the opposite of Europe, building ahead of the curve. It's not overbuilt, it's pre-positioned, and that might pay off big in 3 to 5 years, especially as AI data sovereignty becomes more important for finance, defense, and healthcare.
So where does that leave us? Is the world overbuilt, underbuilt, just misaligned?
Here's the honest answer. We're not in a global shortage, we're not in a global glut. We're in a state of deep structural mismatch. Think of it like this. The US has the most hardware, but is stuck on power and utilization. Europe is efficient, but undersupplied and slow-moving. China is scaling fast, but restricted at the high end. The Middle East is ready, but waiting for demand to catch up.
So we've built islands of excellence. But we don't yet have a global infrastructure network that's synchronized with demand. The next 12 to 18 months will be about balance, matching workloads to regions, optimizing for energy and efficiency, and using what we've already built. Because pouring more money into GPUs doesn't solve anything. If the jobs aren't scheduled, the power's not ready, or the workloads don't land where the infrastructure lives. If you enjoyed today's episode, make sure to subscribe to our podcast on Spotify and YouTube. And if you found value in our discussion, share it with friends, colleagues, or anyone curious about the impact of AI. Spreading awareness is one of the most powerful ways to create a better understanding of this transformative technology. Until next time, keep exploring, keep questioning, and keep decoding AI. This is Emma Clark
And Michael Reynolds signing off from AI Decoded. See you in our next episode.